All right, so let's look at this problem. We've got another problem where we're trying to construct the shear force and bending moment diagrams. So this one's going to have a lot of little changes along the way to deal with. But we're going to first need to do what? Step one, find our reactions. So I'll just call this point over here on the left. I'll try something a little different. I'm going to draw this as the positive shear at A. Okay? And I'm going to draw over here as the positive shear at B. Okay, so I'm drawing these not as reactions, I'm drawing these as shear forces. Okay? This might help you see how when we solve this, how things become positive or negative shear. So to find these values, I'm going to sum moments about either A or B. And to manage it, I'm going to get a concentrated equivalent force for this distributed load. So it's a rectangle, so the area under it would be base times height, which is 4 meters times 4 kilonewtons per meter, so that's 16 kilonewtons. I'm going to sum moments about A, so I need the distance to A. What would that distance be? So I've got 1 meter plus another meter and then 2 meters to get to the centroid there. So that's 4 meters total. So now with all that, I should be able to now sum moments using right-hand rule. That's my sign convention. I'm going to sum moments about A. Make sure I'm in equilibrium. So I should be able to find the shear at B. So all these applied forces are acting down. What kind of moment did they create about A? Positive or negative? Negative. So I'll just work from left to right. So I've got minus 8 kilonewtons times its moment arm, which is 1 meter. Minus 16 kilonewtons, that's the concentrated equivalent force, times its moment arm, which we found was 4. And then over here on the right, 4 kilonewtons times its moment arm, which is 2 plus 4 is 6, is 7. And then the shear at B, which also creates negative moment, times a moment arm of 8. So what is the shear at B? I'm going to need some help for that. 12.5? Negative 12.5. Anybody else get that? So that tells me that my shear at point B is negative. So I'll sum forces in the y direction. In this case, I have my shear at A acting up.
Would that tell you that what you assume?
I assume positive shear at B. So I got a negative, so that means it's negative shear at B. So that means when I draw my shear force diagram at B, it ought to be negative 12.5. So I have my shear force, so up minus the shear at B, and then minus all these other ones. I've got 8 kilonewtons, 16 kilonewtons, and 4 kilonewtons. So what's the shear at A?
40.
Say again?
40.
No. What'd you say?
40.
No.
Just kidding.
28.
15.5.
15.5. I like that better. 15.5. So you guys get that?
Yeah.
I think you forgot to put the negative back in here.
Yeah.
All right. So we're ready to roll. So I'll start by constructing a template, my left edge to right edge. Some things that are going to happen here. I know I'm going to have a change in shear as I go under this one. So let's include that 1 meter in our template. Same reason, that rationale for this side. And then there's nothing going on for a meter, and then the load. So that's another kind of point of interest. So this should help me kind of keep track of all the little bits and pieces. So let's start with the shear. So again, there's my positive x-axis, positive shear, and I'm going to put all my units in kilonewtons. So what is the shear at A? We solved it. It was 15.5, right? Positive. And what was the shear at B? Negative 12.5. So there's my start point and my end point. And let's make it work out. So I know the change in shear between any 2 points is the area under the load diagram, and that the slope of my shear diagram is given by the value of the load. So let's start with just this first little 1 meter segment. So what's the area under the load diagram over the first meter?
0.
0. So there should be no change. I should stay at 15.5. And the shape of that curve is given by the load, and the load is 0, so I have a 0 slope. Okay? Now, as I go from the left side to the right side and go under this 8 kilonewton force, how much does my shear change? 8 kilonewtons. So it should drop down to 7.5? No. Yeah, 7.5, right? So I've got a constant value here. Now the change between 7.5 and this next 1 meter segment is given by the area under the load curve, which is 0, so no change. And the curve connecting those 2 points, well, the slope of that curve is given by the load. The load is 0, so the slope is 0. So I have just kind of a stair step. Now over this interior 4 meters, you can see I have a nice continuous load. So the change in shear there is given by that area, which is base times height. 4 times 4 is 16. So what's 7.5 minus 16? Huh? 8.5? This is not going to be to scale, but it's okay. And the shape of that curve is given by the load, and the load is constant and negative, so I have a constant negative slope. Now what happens? Well, let's look at what happens over the next meter. The change in shear here is given by the area in the load curve. So we go up. What's the area in the load curve in that 1 meter segment? 0. No change. And the slope of the curve connecting those 2 points is given by the load. The load is 0. 0 slope. Now, as I go from the left side to the right side, what's the change in shear? It's negative 4, right? So, hey, what do you know? It matches up. And the curve connecting those 2 points should be given by the loading, and the loading of that last meter is 0, so I have, so there's my shear diagram. Now something happened here that we haven't taken account of yet. What happened? The shear went from positive to negative. So there's a point here where the shear is 0. What happens when the shear is 0? Moment's going to be max. So that's going to be an important point. So let's see if we can find that. I'll call it x1. How do I find that value for x1? Well, we can use our equation. What's the change in moment from this left edge to here? I'm sorry, the change in shear. I start a shear at what? 7.5, and I drop to 0. So that means the change in shear is equal to minus 7.5, right? Over that same segment, let me extend this up. This is the area under my load diagram, right? What is the area under my load diagram? What's the area of that rectangle? Base times height. What's the base? x1. What's the height? 4. Those two things have to be equal, right? So that means I now get an expression that says minus 4x1 is equal to minus 7.5. So what's x1 equal to? Whatever 7.5 divided by 4 is.
So looking at these shear diagrams, over the course of a distributed load like that, is it always going to drop by the value of the equivalent point load?
Yeah.
Okay.
What's the area under the curve, right? The equivalent concentrated load is the area under the curve.
Okay.
And that's what this is, right? The area under the curve. So that's going to give us a little bit of geometry that we need to find the area of this shear diagram and the area under this one. So let's plow ahead and do our moment diagram. Positive x, positive moment. This will be kilonewton meters. Okay, so we're going to start at a pin. Exterior pin has no moment. We're going to end at an exterior pin. It's going to have no moment. You'll notice that to the left of this line, I've got all positive shear. So those will be positive changes. And to the right of this line, I've got all negative shears, which means it'll be negative changes. So I'm probably going to go up to some maximum value and then drop back down to 0. So let's figure out what those values are. And what will help us is to remember the change in moment is the area under the shear diagram, and that the slope of the moment diagram is equal to the shear. So here's a nice little area. It's a rectangle. 15.5 times 1. So that means my moment goes up to 15.5. Let me see if I can write that in. And the slope is equal to the shear, and you can see the shear is constant and positive. So that's a little linear segment. You see that? Now the change in moment over the next meter is going to be this part of the curve, which is 1 times 7.5. I'm going to add that to this. That would give me 23. Is that right? The shape between these points is given by the shear. The shear is smaller than before, so it's a shallower angle, but it's still positive. Again, I'm not drawing this directly to scale, but you get the idea. There is a bend. Now the change in moment from 23 to here is given by the area under this part of the curve, which is going to be 1/2 the base, 1.875, times the height, 7.5. I'm going to need a calculator for that one. Somewhere around 5 or 6. Nobody's getting it.
7.03.
Say again?
7.03.
Maybe 7.03. So we add that to 20 and we get 30.03. That's pretty small. It's pretty much 30, right? And what's the slope going to look like? Well, according to our relationship, it's given by the shear, which starts off positive and drops to 0. So I know I'll have a 0 slope here and a positive slope there, and I'll get a little bit of a curve. Now we're on the downhill side. So the change now will be this triangular piece. So since we found x1 to be 1.875, this piece is going to be 4 minus that, or 2.125. So that times negative 8.5 divided by 2 is exactly 9?
9.03.
Oh, perfect. So we subtract that from this, we get 21. And the shape of this curve will be going from 0 to a negative value. So this is where my graph might get off a little bit. The next segment, the change in moment is given by the area of the shear diagram. That's 1 times negative 8.5. So it's 21 minus 8.5. Hopefully it's 12.5. Is it? And that has a constant slope. In the final segment, the change in shear, or the change in moments area of the shear diagram, which is negative 12.5, that brings us to 0. And again, it also has a constant slope. So again, the curve is not perfect to scale, but you can now do something you hadn't done before. What's the maximum moment in this beam? Yeah, and where does it occur? Not the sentence. It occurs here, right? And that's 1 meter plus 1 meter plus 1.875 meters. So that would be 3.875 meters, which is just to the left of the center line. Any other questions about this one?
When would you have a negative?
When would you have a negative moment? If you had positive forces applied.
Okay, so like if you had forces pushing up underneath.
Right, or a cantilever.
Okay.
Negative forces on a cantilever would cause a negative moment. We had one previously like that, right?
Okay, and that might have been the one that I was out.
Like this one that we just did previously. See, it had all negative moments.
Oh, okay. I see. And you said it was both those online, right?
Yeah.